In the last video, we introduced proof by contradiction, and we did a little example of it, just a very simple example. So all I want to do this lecture is a few more examples. So let's get on with it. So here is the result. There are no integers a and b such that 2a plus 4b is 1. And if you think about this for a moment, it's pretty clear why this is going to be the case. The left-hand side's even, and the right-hand side's odd, and so you can't have an odd number equal to an even number, so this shouldn't happen. And indeed, that's really how this proof is going to work out. So now the negation of this statement is there exists integers a and b so that their sum, 2a plus 4b, is 1. So if we assume this, we're going to reach a contradiction. And that's what we need to drive a proof by contradiction of this result. And indeed, proof by contradiction is particularly good for non-existence results. There is no object so that blah happens. So if we assume the negation is true, that is, the result is false, then we can find a and b so that 2a plus 4b is 1. Well, dividing this statement by 2, it tells us that a plus 2b is a half. But if we think about that for a moment, a and b are both integers, so a and 2b are integers, and the sum of integers is always an integer, and so we've reached a contradiction. Okay, so to write that down a little more carefully, since a and b are integers, a plus 2b must be an integer. That was an axiom that we had earlier on in the course about integers, and so this cannot happen at the same time because this is not an integer, this is an integer, can't happen, it's a contradiction. So because of that, we know the negation cannot happen. So the original statement must be true. So write that up neatly. So to warn the reader, hey, a proof by contradiction is happening, we typically start with a statement like either we use proof by contradiction or assume to the contrary. And that use of the word contrary there is a bit of a key word to tell the reader, hey, proof by contradiction is about to happen. So assume to the contrary that the result here is false. So that means we can find a and b and z so that 2a plus 4b is 1. Well, dividing this by 2 tells us that a plus 2b is a half, but this can't happen because the left-hand side is integer and the right-hand side isn't an integer, and that contradiction tells us that there cannot be integers a and b so that this equation holds. Okay, and that's the proof. Let's do another one. So another no integer solution example, there are no integers a and b so that a squared minus 4b is 3. So let's assume to the contrary that we can find a and b so that a squared minus 4b is 3. Well, let's jiggle this equation around a little bit, and we notice that, well, a squared being 3 plus 4b, well, this right-hand side is odd, so a squared had better be odd. But we did this much earlier in the course that if n is even, if and only if n squared is even, and the contrapositive of that is if n squared is even, then n is even. So if a squared is odd, a has to be odd. We proved that as very early on in the course. And consequently, we can write a as 2k plus 1. But if we insert that, substitute that into this equation, then we can say 3 is, and with a little bit of algebra here, which I suggest you look at carefully, you can say 3 is 4 times stuff plus 1. But this means that if we think about residue mod 4 or dividing things by 4, this tells us that 3 is congruent to 1 mod 4 because I've written 3 is equal to 4 times something plus 1. And that's a contradiction. Okay? 3 is not congruent to 1 mod 4 because 3 minus 1 is not 4 times something, it's 2. So this can't happen. That contradiction is enough to tell us, hey, what we started off at the beginning of our proof, this assumption that we can find a and b so that this is true. That's got to be wrong, and so the original statement is true. And our proof is just pretty much the same thing. So we assume to the contrary that there are integers a and b so that a squared minus 4b is 3. And again, we're using this sort of key phrase at the beginning to tell the reader, hey, a proof by contradiction is about to happen. So we jiggle things around, rewrite this as a squared is 4b plus 3. Since the right-hand side is odd, the left-hand side must be odd, and consequently we know that a has to be odd. Now, if we were doing this very formally and carefully, maybe we would cite a lemma, or we'd maybe put in a little bit more work here to remind ourselves why if a squared is odd, then a is odd. Okay? So maybe we need to put in a little bit more in a proper formal proof. Now, this means that a can be written as 2k plus 1 for some k in z, and then we tell the reader, hey, this means that 3, which is a squared minus 4b, is 4 times something plus 1, which tells us that 3 is congruent to 1 mod 4, which is a contradiction. That can't happen. That's evidently false. And because that's false, our initial assumption here that we could do this, that this could be made to work, that's false. And consequently, there are no integers so that a squared minus 4b is 3. And so the result is true. Okay, let's do one more. And that's going to rely on some definitions about irrational numbers. So take any real number you like. Well, we know that real number is rational if we can write it as a over b, where a and b are integers and b is not 0. So to write this around a little bit, q is rational if there exists a in z, there exists non-zero b, so that q is a divided by b. Well, we know that q, if this doesn't happen, we say that q is irrational. So q is irrational when it's not rational. It's a very fancy notation, or a very fancy name. Anyway, this means q is irrational when the negation of this happens, namely for all a in z and for all non-zero b, q is not a divided by b. And we denote the set of irrational numbers using this blackboard bold I, and of course that's going to be equal to the real numbers that aren't rational numbers, so we can use this set difference. Now this notation here is not entirely standard, indeed there's no really good standard notation for irrational numbers, okay, for various reasons, but we'll use this blackboard bold I in this course. Okay, so our irrational example. If x is rational and y is irrational, then their sum must be irrational. This is a good thing to do by proof by contradiction. And notice what we really have here is for all x and for all y, their sum must be irrational. So this is really a for all statement. And so when we assume the negation, what we're really assuming is that there exists a rational number x and an irrational number y whose sum is not irrational. Now, since we know that x and y are reals, x plus y has to be real. So if it's not irrational, it must be rational. Just to flesh this out a little bit. Okay, so really what we're proving here is that there exists a rational x and an irrational y whose sum is actually rational. That's our assumption. Well, since x and y are both x and x plus y are rational, we can write x is a over b and x plus y is c over d, where all of those are integers, with of course b and d not being 0. But then we can compute what y is just by taking x plus y minus x, and so that's going to be one fraction minus another fraction, which we can write as some other fraction. And of course the denominator here, because b and d aren't 0, that's not 0. And so it's really actually a rational number. But this means that y is both rational and by assumption irrational, which is a contradiction. So that can't happen. And so this can't, so that the original result is true. If we have an irrational number, add an irrational, we always get an irrational. Okay, we write that up nicely. Okay. Here is our statement. A rational number and an irrational number, their sum is irrational. So assume to the contrary that there is a rational number x and an irrational number y whose sum is rational. Well, this implies that x is a over b and x plus y is c over d, because they're rational, with a, b, c, d integers, b and d non-zero. From that, just by doing a little bit of subtraction, y, which is x plus y minus x, is this difference of fractions, and because the denominator isn't 0, the numerator is perfectly good integers here, we know that y is rational. And that contradicts our assumption, just back up here, that y is irrational, and that contradiction tells us, hey, the original result must be true. Okay, let's stop there.